Determine all intervals of increasing trend or decreasing trend and determine the coordinates of all maxima, minima, plateaus, or cliffs for the function f of x equals x times the square root of 8 minus x squared. The first thing to do is find the domain. F of x equals x, a polynomial term, the domain will be all real numbers, times the square root and even root of 8 minus x squared. We can rewrite the square root as a fractional exponent. It will be 8 minus x squared to the first power second root 1/2 power. The denominator of a fractional exponent is the root. It's an even number here, and the domain of an even root is not necessarily all real numbers. The domain requires that what is inside of an even root has to stay greater than or equal to 0. So here, what's inside of the even root, 8 minus x squared, has to stay greater than or equal to 0. We can solve for x by subtracting 8 from both sides. Dividing both sides by a -1, which will flip the inequality. We can take the square root of both sides. The square root of x squared is the absolute value of x. The square root of 8 can be reduced because 8 is 4, a perfect square, times 2. And the 4 can come out as a 2 outside of the square root, and the 2 remains inside of it. We have the absolute value of x is less than or equal to 2 square roots of 2. We can remove the absolute value symbols by putting it between negative 2 square roots of 2 and positive 2 square roots of 2. This will be the domain. It begins at negative 2 square roots of 2. It includes this, a square bracket, and it goes up to positive 2 square roots of 2. It again includes it, so square bracket. The next thing to do is find all critical numbers. We will take the first derivative. F of x is a product of two expressions, so we'll make use of the product rule here. The derivative of the first times the second left alone will be 1 times 8 minus x squared to the 1/2, plus the first left alone times the derivative of the second, which is a power rule. We will bring down the power, leave the inside alone, subtract 1 from the power. I will call that 2/2, and then multiply by the derivative of the inside to complete the chain rule. The first term is 1 times an expression. 1 times anything is that same thing. And in the second term, we can collect the constants together. Everything's multiplied here. 1/2 times a -2 will be a -2/2 or a -1. And we have an x and an x, which will be x squared, and that can move to the front. And then we have an 8 minus x squared, that is to the 1 minus 2 -1/2 power. Since the second term has a negative power, we will need to rewrite it to make everything a positive power. The first term we will leave alone, 8 minus x squared to the 1/2 power, minus, and in the second term, the x squared is to a positive power. It will stay in the numerator, but the 8 minus x squared will move to the denominator to become a positive 1/2 power. As soon as one or more terms in the first derivative have a denominator, we have to combine all terms together over a common denominator to make the first derivative a single fraction in order to find critical numbers. Our first term does not have a denominator. It is 8 minus x squared to the 1/2 power, but we can multiply it by 8 minus x squared to the 1/2 power over itself, a form of 1, so we do not change the value, just the look, but this will give it a common denominator to the second term, which is negative x squared over that same denominator of 8 minus x squared to the 1/2 power. We can now multiply the expressions in the numerator of the first term. 8 minus x squared to the 1/2 power times itself. Since the bases match, we can add the exponents. 1/2 plus 1/2 is 2/2 or first power. So that will just become 8 minus x squared. We can combine it together with the numerator of the second term, negative x squared, because they are now over a common denominator of 8 minus x squared to the 1/2 power. We can combine like terms in the numerator. Minus x squared would be minus 2x squared. And in the denominator, the 1/2 power can be rewritten as the square root. We want to fully factor the first derivative, at least the portion that is not inside of an even root. The denominator is the even root, but in the numerator there is a common factor of 2. Factoring that out will leave behind a 4 minus x squared. We will leave the even root, the square root, alone in the denominator. And the 4 minus x squared is a difference of squares, so it can be further factored into 2 plus x and 2 minus x. Leaving the denominator alone. We have the first derivative written as a single fraction. All powers are positive, so we can now set the numerator equal to 0 and the denominator equal to 0 and solve for all x's. Starting with the numerator, which is already fully factored. The 2 can divide out and does not matter here. But this will lead to x equals to a negative 2 and x equals to a positive 2. Now working with the denominator, the square root of 8 minus x squared equals to 0. We can square both sides because the square and square cancel each other out. 0 squared is a 0. We can subtract 8 from both sides. We can divide both sides by a negative 1. And then we can take the square root of both sides, which will give a plus or minus square root of 8. Now the square root of 8 is reducible, once again, to 2 squares of 2. So this will give x equals positive 2 squares of 2, and x equals negative 2 squares of 2. We want to check and see which of these are in the domain. The domain begins at negative 2 squares of 2. It includes it and goes up to positive 2 squares of 2. It also includes it. 2 times the square root of 2 is larger than 2. And therefore, negative 2 square roots of 2 is more negative than negative 2. And therefore, negative 2 and positive 2 are both in that domain interval. And then the 2 square roots of 2 and negative 2 square roots of 2 are the endpoints, which are included. So those are also in the domain interval. So all 4 of these are critical numbers. We keep them all. We can now draw a domain line, a line representing the domain. Which has a left end and a right end. However, the end points are critical numbers here. And critical numbers are removed from the domain line. And therefore, though it did include, it would have been square brackets. It's not going to include them. They are going to become round brackets on each end as they get removed as a critical number. But the left end is negative 2 square root of 2. The right end is positive 2 square root of 2. And we can put the other critical numbers on here in order. There's a negative 2, and there is a positive 2. This breaks the domain interval up into 3 separate intervals. We can pick a test value in each of these intervals. The square root of 2 is a 1.4. 2 times 1.4 is a 2.8. So between a negative 2 squared of 2 and negative 2.8 and a negative 2, the first interval, we can pick negative 2.5 or negative 5 halves as the test value. Between negative 2 and positive 2, we can pick 0 as the test value. And then between positive 2 and positive 2 squared of 2, we can pick 5 halves. We can now test the trend of each of these intervals by plugging the test value into the first derivative. We don't care about the value of the first derivative, just whether it is positive or negative. So the best place to plug into is the fully factored version, which is this one here. Now, a couple things about this. The denominator, the even root, the domain requires that what is inside of that even root, the 8 minus x squared, up here is greater than or equal to 0. It's a positive number. And the square root of a positive number is a positive number. So that denominator is guaranteed to be a positive number. We're in the domain here. So that will remain positive. The positive 2 in the numerator is also positive, and neither of those will affect the sign of the first derivative. Therefore, it is only dependent upon the 2 plus x and the 2 minus x. Plugging the first test value in, 2 plus a negative 5 halves is, well, negative 5 halves is more negative than negative 2, so that will be a negative number. And then 2 minus a negative 5 halves, which is 2 plus 5 halves, will be a positive number. We have a negative times a positive, which is a negative. A negative first derivative corresponds to a decreasing trend. We can now plug 0 in to the portion of the first derivative that matters. 2 plus 0 is positive. 2 minus 0 is positive. Positive times positive is positive. We have a positive first derivative. This corresponds to an increasing trend in this interval. And now we can plug 5 halves in to the portion of the first derivative that matters. 2 plus 5 halves is positive. 2 minus 5 halves will be negative. Positive times negative is negative. We have a negative first derivative corresponds to a decreasing trend. So we have a decreasing trend in the intervals of negative 2, square root of 2, up to negative 2, and then union, because it happens again from 2 to 2 square root of 2. We have an increasing trend happening from negative 2 to positive 2. The endpoints of the domain are critical numbers. Starting at the left end, we have a critical number. To the left of the critical number, there is no function. But to the right of it is decreasing, and therefore that endpoint will be a relative maximum. So we have a relative maximum occurring at negative 2 square roots of 2 for the x-coordinate. It will have some corresponding y-coordinate, which can be found by plugging that x-coordinate into the original function. So the y-coordinate will be f of negative 2 square root of 2, which will be negative 2 square root of 2 times the square root of 8 minus negative 2 square root of 2 squared, which is negative 2 square root of 2 times the square root of 8 minus negative 2 squared is a positive 4, and square root of 2 squared is a 2. So this equals negative 2 square root of 2 times the square root of 8 minus 4 times 2, which is 8. 8 minus 8 is 0, and the square root of 0 is 0, so overall this is going to be a 0. So it has a corresponding y-coordinate of 0. Right at the critical number of negative 2, we have a trend change from decreasing to increasing. That makes it be a relative min. Has an x-coordinate of negative 2 and a corresponding y-coordinate that can be found by plugging negative 2 into the original function, which will give negative 2 times the square root of 8 minus negative 2 squared, which is negative 2 times the square root of 8 minus negative 2 squared will be a positive 4. So it'll be negative 2 times the square root of 4, which is negative 2 times 2, which is a negative 4. So it'll have a y-coordinate of negative 4. Right at the critical number of positive 2, we have a trend change of increasing to decreasing. That'll make that be a relative maximum. So we have a second relative maximum. It has an x-coordinate of positive 2 and a corresponding y-coordinate that can be found by plugging the positive 2 into the original function, which will be 2 times the square root of 8 minus a 2 squared, which will be 2 times the square root of 8 minus 4, which is 2 times the square root of 4. The square root of 4 is a 2, so that comes out to a positive 4. And then the right endpoint of the domain does not have anything to the right of it because it's the right endpoint, but to the left of it, it's decreasing, and therefore that right endpoint will be a relative minimum. So we have a second relative minimum. It's occurring at an x-coordinate of 2 square root of 2, and it'll have a corresponding y-coordinate that can be found by plugging that x-coordinate into the original function. So y will be f of 2 square root of 2, which will be 2 square root of 2 times the square root of 8 minus 2 square root of 2 squared, which is 2 square root of 2 times 8 minus 2 squared is a 4. Square root of 2 squared is a 2. So this equals 2 square root of 2, and then the square root of 8 minus 4 times 2, which is 8. 8 minus 8 is 0. Square root of 0 is 0, and this will come out to 0, and this will be a 0. So we have our decreasing intervals, the increasing interval, 2 relative maxima, and 2 relative minima.